All right, today we're tackling one of the biggest questions in all of artificial intelligence. It's something that sounds so simple, but the journey to answer it is just incredible. I mean, really think about that. How do you teach a machine, a thing of circuits and code, to understand human language? Well, the answer takes us from something as basic as just counting words, all the way to decoding the hidden history of our language itself. So, first things first, we have to figure out how to translate our language into something a computer can even begin to process. And this is really the crux of the issue, right? You can't just feed a line of Shakespeare to a computer and expect it to get it. We have to convert our rich, messy, beautiful language into the cold, hard logic of mathematics. The very first attempt at this was, well, brilliantly simple. It's called Bag of Words, and it does literally what it says on the tin. It takes a piece of text, throws all the words into a metaphorical bag, and just counts them up. So 2 appears 6 times, the 3 times, and so on. Grammar, sentence structure, all of that context, poof, it's gone. And you can probably guess that this simplicity comes at a massive, massive cost. See, when you throw out the word order, you often throw out the entire meaning of what's being said. And this is the perfect example, isn't it? Dog chases cat versus cat chases dog. They use the exact same words. So to a bag of words model, they look identical. But in our world, they describe 2 completely different situations. And for one of those animals, a much more stressful one. So yeah, we clearly need more than just counting. We need to understand context. And this huge problem is what led to the next great leap forward, a total revolution in how we actually capture the meaning behind the words. The big breakthrough was built on this one powerful idea, which is known as the distributional hypothesis. Just think about it for a second. The words king and queen. They tend to show up near words like royal, throne, and palace, right? Well, that shared context, that's the secret sauce to their similar meanings. So, how do you actually turn that idea into code? The solution is a technique called word embedding. Now, instead of just a simple count for each word, an embedding model learns to represent every single word as a vector, basically a long list of numbers. But these aren't random numbers. Oh no, they are very carefully calculated to encode a word's meaning based on all the different contexts it appears in. So, how in the world does it learn these vectors? Well, a really popular method called word2vec basically gives the model a simple game to play. As it slides a little context window across millions and millions of sentences, it constantly tries to predict which words are likely to pop up near a target word. And by doing this over and over and over again, it starts to learn which words share similar neighborhoods, and it bakes all that learning into those number vectors. And the result is, honestly, it's just amazing. When we visualize these vectors, we get a kind of map of meaning. I mean, look at this dendrogram. You've got Germany, England, and Italy all huddled together. Berlin and Paris are right next to each other. Movie and production are linked up. The model, just by reading text, has essentially taught itself geography and culture. It's incredible. Okay, that's huge. We figured out how to capture the meaning of individual words. But what about our dog chases cat problem? We still need to understand the sequence, the order of the words. We've got these super powerful word vectors, but we're still missing a type of model that can read them in order and actually remember what came before. What we need now is a model with memory. And the answer came in the form of something called recurrent neural networks, or RNNs for short. The key innovation is right there in the name, recurrent. They have this loop in their design that allows information to persist, which creates a kind of internal memory of the sequence it's processing. This is a fantastic way to picture it. On the left, you've got the neat, compact diagram of an RNN with its little loop, and on the right, you can see that same loop unrolled through time. So as it reads each word, it takes in that new word's vector, but it's also looking at the information that was passed along from the word before it. It's building up its understanding one step at a time, sequentially. But, these simple RNNs had a bit of a short-term memory issue. If a sentence got too long, they'd start to forget what happened at the beginning. That's where more advanced versions, like LSTMs, come in. The best way to think about them is that they have this clever system of gates, kind of like a little doorman for information. This doorman learns what new info is important enough to let into memory, what old info is no longer useful and should be forgotten, and how to mix the two together. This gating system gives them a way more powerful memory, letting them understand even super long and complex texts. So we've got meaning, and now we've got memory. And when you put those two things together, well, you can start to decode the incredible secrets hidden deep inside our language. And this is where it gets really, really fun. By pointing these models at historical texts, we can become language detectives and literally watch our language evolve over centuries. I mean, check this out. The word awful. Back in the 1850s, its vector was hanging out with words like majestic and solemn. It meant full of awe. But by the 1990s, it had drifted all the way over to a new neighborhood with words like terrible and horrible. We're actually seeing semantic history mapped out in a visual space. And what's wild is that when researchers analyzed these changes across huge amounts of text, they found language doesn't just evolve randomly. It actually follows statistical laws. For example, the law of conformity tells us that words we use all the time, the really common ones, are more resistant to change. And the law of innovation says that words with lots of different meanings tend to change their meaning a lot faster. Now, speaking of words with multiple meanings, this brings up another tricky question. How can one single vector, one list of numbers, possibly represent a word like tie? It could be clothing, a score in a game, or the act of tying something. Or what about spring? That could be a season, a metal coil, or a creek? Okay, the answer to this is a truly mind-bending but beautiful concept called linear superposition. The best analogy is a musical chord. A chord is one sound, right? But it's made up of multiple distinct notes being played at the same time. Well, a word vector is kind of like that. The vector for spring is like a chord that contains the notes for the season, the metal coil, and the source of water, all held in this one representation. The model then just listens to the music of the surrounding sentence to figure out which specific note to play. It's so elegant. So let's just quickly recap this whole journey. We started with the simplest thing imaginable, just counting words. Then we figured out how to capture their true meaning. After that, we gave our models memory so they could understand sequence. And by putting it all together, we've now unlocked the ability to see things in our own language that were invisible before. And all of this leaves us with one last fascinating thought to chew on. We've just seen how AI can map out the history of our language with breathtaking precision. So the question is, as our language keeps changing in this digital age, what secrets about our society, our culture, and about ourselves will these models reveal next?